Okay, so there's our equations 1 and 2 from last time. And we said in a plane parallel atmosphere, it's an equilibrium. If it's an equilibrium, you can't have energy building up in any layer or declining in any layer because it's an equilibrium, so everything's supposed to stay constant. So that says, just as the flux at the bottom of a layer has to equal the flux at the top, so that says that the radiator flux is constant, and we know it's sigma Tef to the fourth, where Tef is the effective temperature of the star. So it's everywhere equal to what it is at the surface. At the surface, there's no flux going down, it's all going out. As you go lower and lower, there's both downward flux and upwards flux. So the temperature has to rise such that the difference between the upwards flux and the downwards flux always equals the outward flux of the surface. So then, since the radiator flux is constant, its derivative is 0. So then our equation 1 says that the mean intensity equals the source function. And then that now we can integrate equation 2. F rad is a constant, so now if I integrate both sides with respect to tau, I just get 1 over c f rad times tau v vertical object length plus a constant. Last time I called it constant capital C. I'm going to call it capital A because the speed of light's going to keep showing up. Yeah. And it's going to be hard to tell the difference between capital C and little c. Yeah. So we'll call that constant A this time. That would be annoying. Yeah, because it's just like, oh man, so this is a capital C, you know, that sort of thing. Okay, so that's where we were, where we last spoke. Now we're going to make the famous Eddington approximation. So if you're modeling a star atmosphere with a computer, you don't do this. But this is so we can make progress analytically. So Eddington said, let's approximate. It certainly can't possibly be true. But let's approximate in the following way. So Eddington approximation. That I out is constant, and by that I don't mean constant with depth within the star. I mean at any given depth within the star, the outward specific intensity doesn't depend on angle. Okay. It's isotropic in the outward direction.
When you say angle, do you mean both azimuthal and polar?
Yes, I mean both polar and azimuthal angle. Yeah.
So
we would be normally saying azimuthally symmetric. Now we're saying also that it's also that it's the polar angle also doesn't matter. So independent of direction, in other words. Independent of direction into the outward hemisphere, if you will. So in other words, here's some point within the star. And the idea is that we're going to say, just to kind of draw a picture, that the specific intensity, if I represent the direction with arrows and let the length of the arrow be indicative of how bright it is in that direction, the radiation, the specific intensity in that direction, we're saying that it's constant for all outward directions, and we're also going to say it's constant in the inward direction as well, but that it's equal to some different constant. So in other words, I want these to be nice and concentric. So this is just a picture, but in other words, we're saying that the inwards radiation is independent of angle, and the outward specific intensity is independent angle, but it's brighter outwards than inwards, so that there's still a net transport of energy upwards, as there has to be away from the core where it's being generated. Okay, does that make sense?
Yes.
Right now? Okay.
Now I understand this picture. I saw it yesterday in the book.
No, what is that?
Wow, it's a really pretty picture.
But what does it mean?
Yeah.
Right, yes. So that's what it's referring to. Yes, good to see that you're having a look in the book. In is also constant, but it's a different constant. So in this case, the mean intensity, and you can show this by doing the integral over solid angle, and I'll probably have you do that in the homework, but what you would guess and what would be right is that mean intensity is just half of the outward intensity plus the inward intensity. It's literally the average of the outward intensity and the inward intensity.
Because it doesn't depend on any angle.
Because it doesn't depend on any angle, right? So kind of, what else could it be?
So since it's constant, does it also not depend on R?
It does depend on R. So in other words, both I out, both I out and I in depend on R. But they both increase as you go downwards, such that you still have the same net F rad, no matter where you are. So in other words, they both become brighter as you go deeper inside the star, but their difference always amounts to the net radiative flux. They keep a difference such that you always get the same net radiative flux. So everything gets brighter as you go down deeper. If you're at the surface of the star, if you look up, you see the blackness of space, and if you look down, you see, ouch, there's the surface flux. If you go down inside the star, if you look up, wow, it's really bright. But if you look down, wow, it's even brighter. And the difference is always the same as the difference between black and surface flux at the surface. They keep a constant difference.
Ion is like net F rad.
Well, we have to remember that to integrate to get F rad. But what is constant is F rad. So in other words, the outwards flux minus the inwards flux is always equal to F rad. But remember that if it's for isotropic, it's pi times I is what the flux is. So I out minus I in stays constant, multiply it by pi, and that's the radiative flux outwards minus the radiative flux inwards, and that's always equal to the flux at the surface. The net flux is staying constant as you go deeper inside the star. Okay? So, and that's what I was about to write anyway. The radiative flux is pi times the outwards flux minus pi times the inwards flux. So pi times I out minus I in, because remember for isotropic radiation, the outward flux is pi times the specific intensity, and so is the inwards flux. So if it's truly isotropic in every direction, there's no net flux because as much energy is going down through any surface as up through any surface. But here there's a difference between them so that there is a net transport of energy. So in the real star, these would both depend on angle. These wouldn't be constant with angle. It would still be true that if you did the integral over solid angle into the upper hemisphere and the downwards hemisphere, that integral then would give you the flux, and the difference between the two fluxes would stay constant. So the Eddington approximation comes in ignoring the actual dependence on the polar angle that would really be there inside the star. And it's just to make the calculations easier.
I see. So it's
Yeah, it's an approximation to make the calculations easier. Because it's very difficult to do. It'd be essentially really hard to do these calculations by hand, probably impossible. You can do it on a computer, numerically integrated, but by hand it's difficult. So this says that I out minus I in is equal to a constant. So they both keep getting bigger as you go deeper in the star where it's hotter, but their difference stays the same, is the idea. And then there's another relation. So before we had, this is where it's easy to, kind of like, even as I'm doing it, I end up like forgetting, wait, what did we say before? So I made a little note to myself to look back here. So the radiative, so I'll say, now recall that, which really means go back in your notes. And I'll tell you, that's page 68 in my notes that I posted online. This chapter, page 68 in my notes, that the radiative flux is equal to, what was I going to say? It's equal to 4 pi over 3c times I for an isotropic. In other words, if the radiation pressure, if it's truly isotropic, it's 4 pi over 3c times I.
I remember you.
Yeah, so how do we modify it in this case here? Well, it must be that half of it is coming from the outward flux and half of it is coming from the inward radiation. So each of them contributes 2 pi over 3c times I.
Because it's both above and below.
Yeah, because it's both above and below. And so in other words, it must be the case here where we've got one constant above and another constant below, that each of them gives 2 pi over 3c times it. So in other words, it'll be 2 pi over 3c times I out plus 2 pi over 3c times I in will be the radiative flux. I have to get back to where it was. Present case, P-rad will be 2 pi over 3c times I out plus I in, because each of them is giving a contribution of 2 pi over 3c I to the radiative pressure. And since I out plus I in is twice the mean intensity, that means the radiative pressure is 4 pi over 3c times the mean intensity. And going back to our earlier result, if the field is isotropic, the mean intensity is just the intensity, and we're back to 4 pi over 3c I. And it's like we would be for an isotropic. But if it's not isotropic, you have to average I instead of just putting I. Right? Okay? So now we're going to add another equation. And so what this says is thus, and I'm going to put it over here so that we're tabulating the list. Equation 3 will be 4 pi over 3c times I is equal to 1 over c f rad tau v, I'll put that 2 plus a. the equation we had there at the start, where we said P rad was 1 over CF rad tau B plus A. Now we're just substituting what we just found
Very
for P rad.
quick.
Okay, we're just putting in what we just got for P rad.
Okay.
Okay?
Yep.
All right? Because this is one of these derivations that has a bunch of steps and it's easy to like lose with the thread. So I'm trying to keep everything organized here. Because I sit there losing the thread when I'm just looking through it's like, wait, where did that come from? And I gotta go on a scavenger hunt through my notes to remind myself.
It is like that, like even in the book, when they're solving examples, they're like
Right.
referring to equation 325, and I'm like, oh no, this is in a different chapter.
Yeah, oh my god, what is equation 325 again? Right. But of course, it wouldn't make sense to like rederive equation 325, you know. So,
Exactly.
right. But you're like, I have no idea what equation 325 is, and then you go look it up, like, oh yeah, I remember that.
No.
Or you're like, oh, I forgot about that. Let me see how that came about again. Right. So, at the top of the atmosphere, that's where the vertical optical depth is 0, because nothing gets absorbed after that. So the optical depth is 0 at the top of the atmosphere. And, as we've mentioned a couple of times before, I in is equal to 0 because there's nothing above you radiating anymore. So the inward flux is 0. Okay, it's actually the flux from distant stars and planets that are reflecting back on the sun. So the inward flux is 0. So at this location, meaning anywhere on the top of the atmosphere, whole top of the atmosphere, the mean intensity, 1/2 of I out plus I in, is just half of I out. Because basically you're averaging I out in the upper hemisphere and 0 in the downward hemisphere, so it's half I out. The radiative flux, as we found many times, because we're assuming isotropy upwards, the radiative flux is pi times the specific intensity, so pi times I out. So now we can say that the mean intensity at tau b is equal to 0 is equal to the radiative flux divided by 2 pi, because I out is f rad over pi, so half of that is f rad over 2 pi. So that tells us what the mean intensity is at the top of the atmosphere. It's f rad over 2 pi. Are you caught up in terms of your writing stuff down?
Yeah, no. Read the two, where did the 2 come from?
So, the mean intensity is half of I out.
Oh,
I out is f over pi,
So
so half of f over pi is f over 2 pi.
yeah, then.
So now, over here in equation 3, we'll set tau b equals 0 to be at the top of the atmosphere.
Is this like, so like we're treating the top of the atmosphere as an initial condition?
Yeah, we've got a boundary condition at the top of the atmosphere. Yeah, we've got boundary conditions at the top of the atmosphere. We know there's nothing flowing inwards at the top of the atmosphere, so we can make use of that. Yep.
I like boundary conditions.
Like boundary conditions, yep. Yeah, my mantra with quantum mechanics is I always try to emphasize to students that the Schrodinger equation itself isn't what causes quantization. Quantization always comes from imposing boundary conditions on the wave function. So I like to say that it's the boundary conditions that put the quantum into quantum mechanics.
Wow. That makes sense.
It's one of my catchphrases.
Okay.
Setting tau v is equal to 0 in 3 yields that 4 pi over 3c f rad over 2 pi is equal to A. In other words, 4 pi over 3c mean intensity is equal to A, but the mean intensity at tau v is equal to 0 is f rad over 2 pi. So, oh good, now we know what the integration constant is, in other words.
Yep.
So this says the integration constant A, which we got from that boundary condition, is that A is 2 over 3c times f rad. And there's that C that's the reason why I call it A instead of capital C now. So now we can put that into 3. Now we know what A is. So now 3 becomes 4 pi over 3 times multiply through by C on both sides. 4 pi over 3I is equal to the radiative flux times tau v plus 2/3. After substituting for A, yeah, and then multiplying through by C.
The C is gone, so it's independent.
Yeah, so the speed of light's not there anymore. Because it's on both sides in every term, so we don't need it. So, we're getting close to a very important result. This one that I mentioned before about we quote unquote see down to an optical depth of 2/3 in some sense. It doesn't literally mean we see to a depth of 2/3 and no further. It has to be more carefully interpreted than that, but that 2/3 is about to play a big role right there. So, using f rad is equal to, by definition, sigma tef to the 4th. So that's really a definition of tef. That f rad, by definition, is sigma tef to the 4th power. We can say that the mean intensity is equal to 3 sigma over 4 pi tef to the 4th times tau v plus 2/3. So here I multiply by 3 over 4 pi.
And
So
substitute.
sigma tef to the 4th for tau v. Okay? But wait, we're not done yet. We've got another approximation we're making, local thermodynamic equilibrium. So, assuming LTE, which means, remember, that you're assuming that the photon mean free path is short compared to the scale over which the temperature changes appreciably, which isn't always a great
we can
approximation.
ignore the tau v.
No, that's not it. We're just assuming that photons thermalize. That, in other words, photons undergo many interactions, if the mean free path is short compared to the distance over which the temperature changes appreciably, then as photons are bouncing around, getting scattered and absorbed and so forth, they're pretty much doing so in a region that is very nearly at constant temperature, because they bounce around many times, if you will, before they would get to a region where the temperatures changed a lot. So in other words, they have the opportunity to bounce around a lot and thermalize, come into thermodynamic equilibrium with the gas in their vicinity. And if they come into thermodynamic equilibrium, that means they have a Planck spectrum. They have a black body spectrum. So LTE, assuming LTE means you're assuming that the radiation is very nearly a black body radiation at every layer. It's changing with temperature, so the black body radiation is different at different depths because the temperature is changing. But we're basically saying the radiation down where the temperature is 10,000 Kelvin is pretty much a 10,000 degree black body. Where it's 5,000 Kelvin, it's a 5,000 degree black body, and so on and so forth. But the sun, that doesn't happen because it tops out at 50 or bottoms out at 5,800 Kelvin. But that's what I'm getting at there. So assuming LTE, we have the mean intensity is equal to S from 1, remember that we have. And on top of that, remember that we said that in LTE, the source function is equal to the Planck function. S lambda is equal to B lambda.
Yeah.
In LTE. So the integrated source function, which we call capital S, integrate over all wavelengths of S lambda d lambda. In LTE, we get to make the approximation that S lambda is B lambda. So I integrate B lambda over all wavelengths.
And you get S equals B.
And you get sigma t to the 4th over pi. Because the integral of B lambda d lambda is sigma t to the 4th over pi. But this is in TEF, this is the local temperature. TEF refers to the radiation we're getting out of the surface, and that's not even the temperature of the surface layer. It's the overall temperature, if you will, of the radiation coming out of the star, which is coming from many layers. It's coming from many layers. So what we see is a sort of average over radiation coming from many layers within the star. So T here is the local T as a function of R. That's what we mean by that T. And we're about to get the result we've been after. And thus, T to the 4th is equal to 3/4 times TEF to the 4th times tau b plus 2/3. So in other words, what we're doing here is plugging back into here. The mean intensity is equal to S, which is sigma t to the 4th over pi. So we plug sigma t to the 4th over pi for the mean intensity on the left-hand side of that equation over there. Multiply through by 3 over 4 pi. And that gives us the t to the 4th is 3/4 TEF to the 4th tau b plus 2/3. And this is a very important equation that we draw a box around, and we will remind ourselves that this applies to a gray atmosphere. In other words, we've integrated over wavelength. We're not looking at wavelength dependence. Gray atmosphere. We also made the Eddington approximation. And to top it off, we also assumed LTE. So making all of those simplifications, we got this result. And again, this T is a function of radius, or alternatively optical depth. This is how the temperature changes with optical depth as you go below the surface. The vertical optical depth as you go below the surface.
So, okay, so this T is a function of both R and tau sub V.
Well, remember that
Tau
tau sub V and R are just different ways of expressing position below the surface.
Okay.
So it's not a function of both of them. It's a function of take your pick of them, because tau V is a function of R. So in other words, R at the top of the atmosphere is like, the radius of the star, and as I go down, okay, then R is decreasing as I go down, but tau V is increasing increasing as I go down. Sorry, tau V is, so I should still draw it down. The optical depth is increasing as you go down, because it's zero at the surface, and the further something is buried, the bigger the optical depth it is, because more and more of the light from it isn't reaching you because it's been scattered or absorbed along the way. So remember that optical depth increases downwards from the surface, whereas radius is measured from the center of the star, so radius decreases as you move away from the surface. Now, you could also say, I'm going to call literal distance below the surface Z, let's say, and that Z would be increasing and tau would be too, but tau is a function of Z, right? In other words, it's typically kind of exponentially increasing with Z. So this is T as a function, if you like, of the optical depth. We can kind of say T of tau V to the fourth power has this formula. It's 3/4 Tef to the fourth times tau V plus 2/3. So you can't take this too literally, because we made all these approximations. But notice, in these approximations, the surface temperature isn't Tef. The surface is where tau V is equal to 0. So there, the surface temperature, T surf to the fourth power, will be given by 3/4 F to the fourth times 2/3, right?
So it's half times.
So in other words, right, so in other words, it's half of Tef to the fourth. So in other words, the surface temperature is the fourth root of a half times Tef. bit smaller than TEF. Also,
which is expected,
what's that?
I said which is expected, right?
Yeah, it's, so, because the idea is that we are, if we're looking down into the star, okay, then let's say here is the top of the atmosphere. You can think of it as, in your head, divided up into a bunch of thin layers. And you're getting radiation from each of these thin layers. The further down you go, the less of that radiation makes it to you before getting scattered out of the beam by intervening layers. So you get you get virtually all the radiation from this thin layer at the top of the atmosphere, a little bit less from this layer, a little bit less from this layer, a little bit less from this layer, and so forth, okay? But these layers are increasing in temperature. So the radiation you see is a blend of radiation from layers of increasing temperatures as you go down, but less and less of the radiation from each layer as you go further down into the star. Not you, but in other words, you're up here all the time. But as you mentally say, how much radiation am I getting from down here? The temperature keeps rising. So what you see is a blend of radiation from layers of different temperatures. And so here's the big result that comes out of this. At the level where the vertical optical depth is equal to 2/3, we have that T equals TEF. Because if you go back to our relation, it's T to the 4th is 3/4 TEF to the 4th plus 2/3. So if you put in tau equals tau v plus 2/3, if you put in tau equals 2/3, you get 2/3 plus 2/3 is 4/3, and 3/4 times 4/3 is 1. Is 1.
Wow.
Yes.
That is so cool.
Uh-huh.